Please join me in welcoming to the Distinctive Voices podium, Dr. David Valentine.
Thank you, Susan. Can everybody hear me? I think we have one mic on now. Thank you, Susan, for that. That was pretty much a synopsis of my talk today. So I will touch on each and every one of those things in a little bit greater detail. Now, in preparation for coming and speaking to you, I spoke to my introductory oceanography class this morning, average age about 20, and asked them, first, how many of you have heard of the Deepwater Horizon oil spill? And about 25% of them had heard of it. 75% had not. So that was one important thing that I learned giving this practice lecture for them this morning. The other one was that my humor is in great need of help. So I apologize in advance. So I am going to talk about exactly what Susan outlined for you. And before I begin, I want to make a point that no matter who is found to be at fault for this incident, whether it's BP or whether you want to blame the administration, whether it's the BOEM, the agency that oversees regulations, or the human error that invariably led to this, this event is really attributable to our need for fossil fuel in our society. And as long as we have that need, we can expect to continue to see these sorts of events. And they have continued since. There's a large gas leak in the North Sea as we speak. Chevron has had a number of problems offshore Brazil. And it's something that we need to be aware of. We need to try and address as best we can, both with usage and with environmental regulation. So that aside, I want to talk to you today, and this is the outline. I'll start with the background, why this happened in the Gulf of Mexico, what were some of the technological innovations that led us to this, and then I'll talk about my own personal experience in becoming involved with this spill and the science of this spill. Then I'll focus for a while on what we've learned, and I'll talk about 5 different studies that we have published that look at particularly what happened in the deep ocean during the spill. And then, time pending, I will give a bit more of a 2-year update on where things stand now. I will use the term we extensively. There are a lot of contributors and collaborators, and I just list a few of them here. John Kessler from Texas A&M, Molly Redmond and Igor Mezik, both from UCSB, Chris Reddy, Rich Camilli, and Liz Kujawinski, all from Woods Hole, and Tom Ryerson from NOAA. There are also, I counted earlier, 49 co-authors that I've published Deepwater Horizon work with since then, and I will at least list each of their names when I talk about the work. There's also the behind the scenes of getting out there and doing the science, and that could not have happened without a lot of effort from the National Science Foundation, who was able to mobilize not only resources in terms of funding, but to mobilize vessels to get scientists to the scene to study what was happening when all other vessels were being used for other purposes. So the background of the Gulf of Mexico, it is located down here. There are 5 states that border the Gulf of Mexico that have shoreline. That's Texas, Louisiana, Mississippi, Alabama, and Florida. And it's really this northern region of the Gulf up here that I am going to be focusing my talk on today. This is an oil-rich region, and roughly 1/3 of our oil comes from offshore production in the Gulf of Mexico, our U.S.-produced oil. Currently, there are over 3,850 active platforms in the Gulf of Mexico with over 50,000 wells drilled since 1947. And you can see this tremendous saturation throughout this area, which is the shallow water. You can see a little bit here that this is the break where it goes from shallow water down to deep water, and roughly 1% or less of the platforms are currently in the deep water. That's not because there isn't petroleum reservoirs there. That is because the technology is just advancing to the point where we can go after oil in these environments. So much of the oil in this region, the highly saturated region where all these wells are, has been tapped. There's that supply is dwindling, and so there's a push toward deeper and deeper environments to look for oil. that is enabled by technologies. Off the coast of California, we have fewer than 40 total platforms, less than 1% of what's in the Gulf, and they are all fixed structure platforms, such as those shown over here at the left. They're attached to the seafloor, and as I tell my undergraduates, if somebody tells you that they're moving, then you should be skeptical. I won't go into what I actually say. The technologies that have allowed for deeper and deeper platforms, first there were the fixed structures, then a move when you're getting to 1,000, 1,500 feet water depths of structures that sway a little bit with the currents. The move after that was to floating platforms that were moored to the seafloor with a number of large sea anchors so that they would sit in place, but they were fundamentally floating. With the development of advanced global positioning enabled by satellites, platforms don't need to be attached to the seafloor anymore. And so now we have a class over here known as the Mobile Offshore Drilling Unit. They are held in place by opposing thrusters that just keep them in one position, and they're referenced to the satellites flying overhead. They only need to be attached to the seafloor by this pipe that they do for their drilling and the extraction of the oil, commonly referred to as a riser pipe. This is the type of platform to which the Deepwater Horizon belonged. And on April 20th of 2010, there was a series of problems beginning in the reservoir where gas came up. It broke through the seal that they were trying to put to seal that well off, and it broke through. It shot up the pipe, and the gas emanated at the rig and caused an explosion. That explosion was visible for over 35 miles. It was a massive explosion. It took the lives of 11 people. Many people did survive and jumped off the platform. And the platform caught fire, and it burned for 2 days until the 22nd of April when the platform sank. Now, it was still attached by that pipe to the seafloor. And when the platform came down, it came down just a few hundred yards away from where it started, but that pipe was bent and torqued and broken in a number of places. Normally, there shouldn't have been oil flowing out of that pipe because there's a fail-safe at the seafloor that's a large valve known as a blowout preventer that is supposed to prevent the flow continuing if something catastrophic happens at the surface. However, what seems to have happened is that pipe from within the earth that had been laid as part of that well shot up into the blowout preventer, and multiple pieces, so that when the valve, what are called shearing rams, were supposed to seal shut, they got caught on that pipe and they got torqued a little bit. So there were openings where the oil could still flow through the pipe. And as a result, there was oil flowing out of the well, through the pipe, and coming out in all the different broken spots on the pipe. In early June, this video was taken. At this point, they had cut away that pipe, and it was all coming out from the top of that valve, that blowout preventer. And this is a HD video of that flow coming out. So this is what the view was from a remotely operated submarine on the seafloor. The flow rate here is about 110 liters per second of oil, and not quite as much gas, but a similar amount of gas. That's roughly enough to fill the tank of your car in about a third of a second. That's how fast it's coming out. What was not well known at the time, that I became aware of very early on and suspected, was that there was a significant amount of gas. And by mass, between a quarter and a third of the material emanating from that pipe was natural gas, which behaves very differently than oil does. Methane is the main component of natural gas. By mass, it was somewhere between 15 and 25% of the total amount of material that emanated from that well. The other components, and I'll talk about them in greater detail, are known as ethane, propane, and butane and pentane. I'll talk mainly about methane and propane to try and keep the hydrocarbon naming simple. So as the material emanated from this pipe, it shot up and it was atomized, meaning very much like an aerosol can. As it shot out, it became tiny little droplets. And that's important because droplets can get stuck in water even if they're buoyant. And the reason that happens is because the droplet size becomes so small that that droplet lacks the buoyancy now to force apart the water molecules above it and to rise. So those droplets can become stuck in the water. And there had been some modeling done on this effect by Scott Sokolowski and Eric Adams that they'd published in 2005. When this event happened, they were given a share of the Ig Nobel Prize, sort of the Nobel Prize each year. They shared it with BP for disproving the commonly held notion that oil and water don't mix. This effect was apparent very early on, and the ROV pilots who were going down to the ruptured wellhead and were looking to see where the pipe went and where the wreckage, the hull of the Deepwater Horizon was, they noticed that there was something going on in the water between about 1,000 meters and 1,300 meters depth. That's roughly 3,000 to 4,000 feet. The well itself was about a mile deep at around 1,500 meters water depth. And what they noticed, this is a picture from Science magazine, or the journal Science, was that as you descend down and you look through the camera of your remotely operated submarine, the water is blue as it should be until you get down to around 1,000 meters. And then it starts to become a murky brown. They knew that something was going on. This was clearly related to the spill. And in fact, it's thought to be because of this effect that Sokolovsky and Adams had published on. This is a laboratory tank experiment. This was provided by Rich McLaughlin and Roberto Camasa at University of North Carolina, Chapel Hill. And what it is, it's oil is going to come shooting out here and be atomized, and it's going to come up. And there's that oil is buoyant. It should go all the way to the top. But there are two different liquids in here with different densities. The oil is more buoyant than either of those liquids. But what's happening is that oil is becoming atomized. It's picking up that denser fluid, and so it can't penetrate up. It's getting stuck at the interface where there's this steep density change. So if you just let that oil out in droplets, it would go all the way to the surface. But it doesn't. It gets stuck down in the deep water because of this entrainment effect. So that's what was happening in the deep water. And I want to step back now and talk about, as a scientist, how I became involved in looking at this process and the contributions that we were able to make. So my basic interests, I was trained as a chemist, and I came here and studied Earth system science with Bill Rieberg. And my interests have always been in microorganisms and their metabolism, how they can impact the Earth system on a very large scale. This is a picture of seawater. The large bright dots are bacteria, and the small dots are the viruses that infect the bacteria. There are roughly 50,000 bacteria in each teaspoon of seawater, and roughly 500,000 of their viral predators. It's a staggering amount, and in those organisms there's an exceptional diversity, both in who they are, but also what they can do and what their capabilities are. And so this is what has driven me scientifically to understand these processes and these metabolisms. Most of my work has focused on the greenhouse gas methane, and the production and consumption of methane, particularly in the ocean environment. And that's work that I started here, and then it's spread out to look at some of these other hydrocarbon gases, at oil and at other compounds. Most of this work is performed in the deep ocean. And this is a site I drove about 15 miles from it on my way down from Santa Barbara today. This is off the coast of Redondo Beach. It's at 2,500 feet water depth. And what you're looking at is a photomosaic, and I'm going to fly through it in a minute, of 40,000 different images. It's about 400 meters across, to give you a scale. 40,000 stereo-paired images taken with an autonomous underwater vehicle of this environment. And what's happening in this environment is that methane gas is penetrating up from the subsurface and creating these microbial terrains at the seafloor. And so we'll fly through so you can see what some of these terrains look like. And those images are draped over the bathymetry that we also simultaneously collected. So these are the sorts of environments where we work and the kinds of processes that we're interested in, the microbial processes, the chemical processes. So when the Deepwater Horizon occurred, it was something that I was clearly very interested in and wanted to contribute to in any way that I could. How I actually got involved was really more of a matter of happenstance. Earlier that month, I'd published a paper in the journal Nature Geoscience, highlighting the discovery of a series of asphalt volcanoes off the coast of Santa Barbara. And somehow, I still don't quite understand why, this got picked up by the media. LA Times wrote about it, BBC, a couple other entities. These volcanoes, this is the biggest one here. It's at about 600 feet water depth, measures about 400 feet across and 60 feet high. So giant mound of asphalt sitting on the seafloor. And it picked up some interest. So less than a week later, after this paper came out, and I talked to a number of these reporters, the Deepwater Horizon happens. And who are they going to call to get information about oil and gas coming out on the seafloor other than the guy they talked to last week about the giant tar ball? And so in one of those early conversations, one of those reporters asked me about containment strategies and explained to me what BP was proposing for containment strategies. And so I gave her my best assessment of what the problems they were facing were. And when I saw the design, I gave them my assessment of why I thought it wasn't going to work. The basic reason is because when gas comes out from a reservoir under, it's really quite hot, but it cools very quickly when it hits the ocean water. And when you have the combination of natural gas and the high pressure of being a mile deep in the ocean and the cold temperatures, ocean temperatures about 4 degrees Celsius, 40 degrees Fahrenheit, there, it immediately forms a solid phase, an ice that basically traps the methane in a lattice of water. And that happens almost immediately. We see it in all the sites we work at. So it was clear to me that this was going to be the main problem that they were going to face and that they needed a solution to it if this was going to work. This was April 30th. And then a little over a week later, it failed for this very reason. Because of this gas hydrate, this solid methane ice forming, sticking in the pipe and just clogging the entire thing. So basically, May 8th, 2010, my summer was over, and it hadn't even begun. I was still teaching, but suddenly I was thrust into this in a way where I was getting a lot of, being asked for a lot of comments from the media as to what was going on. So over the next month, there was a lot to do, and there are a few things I focused on. One was that I wanted to make the scientific community aware of the gas content and the issues they were going to have with gas during the spill, and really make the point, 2 points. One, you could use it to quantify how much was coming out, but also that this was going to be the feature that distinguished this event scientifically from any other spill that had happened. And at the end of that month, the end of May of 2010, I published this opinion piece in the journal Nature. I was also working with my congressional delegation. You can't quite see this. I swear it says Congress of the United States. Lois Capps is my representative, and I worked with her office to try and get information, just fundamental information about what was really coming out of that well, what was being done, what the dispersant was, those sorts of things. And then lastly, I worked with the National Science Foundation to try and get funding and resources to get out there and begin doing science. And in sort of topsy-turvy world that this was at the time, I received the first of what NSF calls a RAPID award. And this is, in the scheme of awards, it's pretty small, around $100,000 in a budget of $5 billion for the National Science Foundation. And it made the New York Times that they'd given this award. So that's a sort of strangeness that was going on at the time. I also, during this time, was developing the scientific motivations. There was an aspect of trying to help and trying to understand what was going on and informing the public, which was desperate for information. And there were also scientific questions that were festering. And those motivations were basically what's happening to the oil, particularly in the deep water, what's happening to the gas, what are the microbes doing, what are their impacts, and what is happening to all that dispersant. And so that's what I set out to try and address and what I'll walk through here today. So the next step was to go out on expeditions, and I've been on 6 expeditions total, I think. I've lost track. My wife could undoubtedly tell you how many they've been, the longest being a month. But these were unlike any expeditions I'd ever participated on. First, we had the research vessel Cape Hatteras, which this was a National Science Foundation funded cruise. They provided that vessel to us. And then the next 2 that I'll talk about were on the NOAA ship Pisces, which is there below. The reason that these were so different is because I've never given a press conference dockside. And here you can see this is Admiral Z, the regional area commander. and we're giving a press conference talking about all the many places that he expected us to go. For those of you who know the map of the Gulf, that's impossible. And below is Admiral Thad Allen using our vessel as a backdrop. They came offshore with reporters to have a press conference and used our operations as a backdrop. So just things that you're sort of unprepared for as a scientist. On site, it was not any less hectic. This is an image of where the ruptured well is. That flame is about 100 feet high. And that is some of the gas. Roughly a quarter of the gas that was coming out of the well was being siphoned off at that time and burnt off in that flame. But there were hundreds of vessels, and it was very busy with a lot going on. At times, it was even apocalyptic with the collection of oil and the surface burning that we saw. We naively thought that we could help to inform the public by having media days on our cruises. And this is an example of a media day where you can see the chief scientist over there in the right corner being sequestered by a couple of BBC reporters, an Austrian reporter there in the middle talking to an Austrian scientist that we had aboard, a water taxi pilot, a producer, a cameraman, and then this poor graduate student here in the middle trying to actually do the science. So, you know, we at least succeeded in getting some information to the public, if not losing our minds for a couple of days of these operations. But what we were really there to do at this point was to study these deep water plumes. And there had been a lot of controversy coming from the scientific community, coming from the companies that were involved, coming from the federal government, and in terms of what a plume was and defining one. This is actually an unfair characterization because that statement, he's not referring to what was emanating from the wellhead. He was referring to what was being trapped in the water in these intrusion layers, although it does make for a comedic satire. So we were there trying to understand these, and the first thing we wanted to do was understand the missing oxygen. Oxygen was being used, and we wanted to understand what it was that was being coupled to that oxygen in order to predict how that oxygen loss may continue over time. And there was concern then about massive oxygen loss and kill-off of organisms, so that was our first target. What's driving the oxygen loss, and what's going to happen to it? And so this is, I won't show too much data in this talk, but I do have a series of slides just outlining our approach. Here, what we have is a classic oxygen profile for the ocean. What we're looking at is oxygen concentration on the x-axis, and on the y-axis, we have depth in the ocean. So this is the sea surface here, and then this is going down, and a mile is about here. This is a very classic. Most of this profile for oxygen is very classic. Oxygen tends to be high in the surface water. This is because there's plants that live up there and photosynthesize. They produce oxygen, and it can actively exchange with the atmosphere, so oxygen is high. And then as you get down to 500, 600, 700 feet, you don't have enough light to drive photosynthesis, to produce oxygen anymore, but you do have a lot of dead material and fecal matter falling through the water that is being consumed and respired and using oxygen. So you get this oxygen loss. It tends to fall to a minimum at around 1,000 or 1,500 feet, and then it begins to increase again. And the reason it increases is because these waters are coming from somewhere else on the planet. They're coming from the polar regions. They're much colder, and they can have more oxygen in them. So these are waters from somewhere else that are populating down here. What's unique about this profile are these big declines here. These are not observed anywhere, really, except during this spill. These massive and severe oxygen anomalies, as they were often called. So we wanted to understand what was going on with these oxygen anomalies. This is one-dimensional view. This is one location in the ocean. Here is 6 locations in the ocean, giving at least a bit of a two-dimensional view. On this particular cruise in June of 2010, occupied 31 different stations or locations around the wellhead. This is the location of the wellhead. And this contour is showing a slice across here where we measured the oxygen anomaly at each of these locations and then contoured it. And so what we see is this anomaly down here, in this case centered about 1,100 meters water depth, and fairly significant. With this missing oxygen, there was also oil and a whole lot of natural gas. the amount of natural gas in these depths was roughly 100,000 times the natural background level. And in some cases, it was higher in absolute concentration than the oxygen itself, meaning if you carefully degassed that water, you could pretty easily make it blow. We didn't do that. It would have been great for YouTube, probably would have gone viral, but we didn't. And so we were interested in linking these hydrocarbons. We knew the hydrocarbons were causing the oxygen decline, at least that was our hypothesis. So we wanted to understand how that was happening, and particularly which hydrocarbons were involved. We focused in on the gases because they were highest in concentration. Gases dissolve very readily, otherwise fish couldn't breathe. So gases, including hydrocarbon gases, dissolve very readily in water, and so they were our first target. And what I'm looking at here is propane, and I'm comparing the ratio, this is methane, and comparing its ratio to propane. In a reservoir, or in a source, this should be constant. That is, it's going to have one ratio. And the fact that it doesn't tells us that something's going on to change that ratio. So this is just one view of it where we're comparing that ratio to the absolute concentration of methane on the y-axis out to extremely high concentrations here. And based on this and other data, we surmised that in the reservoir, in the source that was coming into the water, the ratio should be something around this value here. It turns out, once that data became available, that we were very close in our analysis. And so we only have a few data points that actually fall along that line. If you dilute, if you take water that has this gas dissolved in it and you dilute it, it will move it down this way. It'll move it down the line here. It won't change the ratio, but it will change the concentration. We see very little data that follows that trend, and instead it all moves off to the right, showing a preferential loss of propane over methane. And that can be attributed to biological oxidation, where this deviation you can, from the deviation, figure out the absolute amount that was consumed. And so we did that, but we also wanted to double check our logic, and so we compared that. That's shown down here. We figured out the amount of propane consumed, and we compared that to the isotope heaviness of what was left. And this requires a little bit of explanation. First, this is not a mess up. This says isotope anomalies, but I put it in Cyrillic because isotopes are Greek to most people anyway. But what happens is that when an organism, particularly a bacterium, consumes a hydrocarbon, they preferentially eat the lighter isotope first. They eat it more quickly, and as a result, the isotope heaviness increases. Isotopes are atoms that have the same number of protons, different number of neutrons, so they have different weights, and the lighter one gets eaten more quickly in this case. So as the consumption occurs, which is shown here, consumption moving this way, you expect to see an increase in isotope heaviness, which is what we see going off this way. So this is the trend that we would expect. And a couple things in this line. The slope here is an inherent biological preference factor, if you will, for the bacteria. And that happens to match the only other measurement for that preference factor that we had made 3 years earlier in collaboration with Stan Tyler, who was then here at UC Irvine. The intercept should be equal to the initial reservoir composition, the amount of isotope in the reservoir material, and we were spot on with that estimate in the final analysis once that data came in. So this was very supportive of our interpretation because these are completely independent measurements. But still, we wanted to demonstrate that biological activity, and so we did a few things. This is one example. We took fresh samples from these deep plumes. We fed pure isotopically heavy propane to them, and then we looked at the respiration product as it was produced. In this case, looking time course of 24 hours, and what we see is, again, an increase in isotope heaviness, here shown as respiration, over that time course. And when we added something to kill them, you don't see this activity, so it's clearly biological activity. So we were pretty confident that this approach was working, and what this allowed us to do was to compare the amount of propane that was missing for any given sample to the amount of oxygen that was missing. And when we compared the missing propane to the missing oxygen, what we found was a reasonable relationship indicating that up to 60% of the respiration was from propane. That is, 60% of the missing oxygen was coming just from propane. Another 10% was coming from ethane, and probably the remainder was coming from butane and a few other select compounds. But propane was really driving the show in these early days. This was the first paper we published. It came out in September of 2010, before the first relief well was even completed, under the title Propane Respiration Jumpstarts Microbial Response to a Deep Oil Spill. And it was relayed to the public, I think, in an accurate way. Natural gas from ruptured well remained trapped in Gulf waters. That was true. The gas was being trapped. And that bacteria digested gas, not oil. I think that was also accurate. So having addressed that initial issue, we went after the next issue, which is really the 400-pound gorilla in the room, and that is what was happening to methane, the single most abundant component that was coming out. This says, you know what's starting to sound really sexy around here, methane, for those of you who can't read it. We knew that methane was not making it from the wellhead, and we saw that in our data. We also had made some other measurements, and this is not a paper that I was involved with. This is a ship track from our June cruise, and what was happening here is that methane was being measured in real time as the ship worked its way around the wellhead. And this was published by Sherry Von Lewis. I was not an author on this paper, and I'm somewhat ashamed to admit that my sole contribution was choosing those track lines. It's not exactly what you would ideally pick from the start. But what we found is that very little methane was coming out. Less than 1/100th of 1% was coming to the atmosphere. So it was being trapped, and this was confirmed also by overflights from the National Oceanic and Atmospheric Administration. So I don't have a whole lot of other graphs. I just wanted to walk through the logic on that one. But I do want to talk about some of our subsequent findings. When we went back, that was in June of 2010, and we went back as part of the response effort in September and October of 2010 on a series of 3 cruises, 3 research expeditions, and we covered quite a bit of territory, and this was on the NOAA ship Pisces. This is the wellhead shown up here, and each of these dots are locations that we visited. And so we made it out well over 200 miles from the wellhead, chasing the plumes as they matured. And so what we were after in this case was the methane. And so we went armed to measure methane shipboard. And after several days, we found the plume. We found all the indicators of the plume. We found that there was oil still in the water. We found the oxygen anomalies. It turned out, I'll show you later, there was dispersant there too. So we found the plume, but there was no methane. And so several days in, we sat down and said, okay, what are the chances that all of the methane has been completely consumed? So that became our working hypothesis for the remainder of these 2 cruises. And what we set to do was to test this hypothesis. And so we sat down in the galley of the ship, which rarely in science do you ever sit down on a ship and design a hypothesis and then test it and write another paper about it within a couple weeks of coming home. You just don't, not a chance that you very often get. So we set out and we figured out we had 4 reasonable tests of our hypothesis. The first was to simply continue measuring methane everywhere we went. If we found it, we disprove our hypothesis and we have something else to do. The second was to look at all the missing oxygen and to take all these profiles of missing oxygen and to integrate them to add up the total amount of oxygen that was missing in the Gulf of Mexico from this spill. And then ask the question, is that enough oxygen to account for the bacteria consuming all the natural gas? That was our second test. The third test was to look for the methane-consuming bacteria. Really, they're the residual community. They would have grown, they would have eaten all that food, and they're not just going to disappear. So we should still see some residual community. So we also tested for that. And then lastly was to develop a model, an interpolation, to figure out, is this even reasonable? Can things really happen this fast in the deep ocean at 40 degrees Fahrenheit? So what we found was startling. We didn't find any methane. 671 samples from 105 locations in the plume, above the plume, below the plume. We didn't see any high concentrations of methane anywhere. We were able to figure out the oxygen anomaly, and this is a contour of the missing oxygen in the Gulf. The plume, by this point, had moved down to the southwest. And what we found was that there was roughly 1 million tons of oxygen missing from the Gulf of Mexico. And that is enough to account for the consumption of all of the methane, as well as the other gases and some fraction of the oil. Can't say exactly how much of the oil, but some fraction of the oil can be added in there. When we looked at the microorganisms and we sequenced the DNA from the microorganisms, we found that the community that was there was largely methane-consuming microorganisms. They're very unique, they're easy to identify, and they were there and abundant without any methane. And lastly, the model showed that this was all reasonable. It pushed what we know for biology, but not too far. And so we published this in January of 2011. Also in Science, a persistent oxygen anomaly reveals the fate of spilled methane in the deep Gulf. And I think this also got relayed to the public in a reasonable way, that the methane had been consumed. I don't know about mopped up, but the rest of the article was pretty good. So the third thing that we wanted to look at, so that was two. The third thing we wanted to look at was what was happening to the dispersant. And this is a picture I took out of Port Fourchon. The dispersant was produced by a company called Nalco. It's known as Corexit. And 771,000 gallons were added at the ruptured wellhead, with over 1 million gallons added at the sea surface, mainly by airplanes. And just to give you a scale for that, these are trailers that go behind semi-trucks. These are Nalco trailers that presumably were carrying dispersant. There must have been a whole lot of these to get to 771,000 gallons added in the subsurface. And this was being shot from a wand into that flow of oil. In fact, the only reason we have all that video is because they were taking video when they were adding the dispersant at the wellhead. This effort was really led by Liz Kujawinski at Woods Hole, because she developed a technique to quantify the key ingredient in the dispersant. It's a component called DOS, or dioctylsulfosuccinate, for those of you who are chemically inclined. She was able to measure it with several orders of magnitude greater sensitivity than the EPA method that was previously available. So she developed this method during the spill and used it on all the samples that we collected for her in these expeditions. Around the wellhead, so this is the wellhead again up here. This is that oxygen map I showed you before for reference. During the spill in June, the spill was still active, we saw dispersant throughout the wellhead. And these concentrations, the color and size indicates the concentration, where this is about 10 parts per billion, which is not a really high concentration. And each color drops down about an order of magnitude, 1 part per billion, 0.1 parts per billion, 0.01 parts per billion. So these are certainly measurable, but nothing above the EPA benchmarks for toxicity for these kinds of things. But still, a significant amount was there. When we went back and looked in September, we were surprised to find that it was still there. It had diluted extensively. It had now traveled over 200 miles. It was actually all along this track, this 200-mile track between the wellhead here and this is almost getting offshore Texas. So there was still dispersant there. And this was surprising because the assumption had been that the bacteria would eat the dispersant as well, but it clearly persisted. It hadn't been applied for several months at this point in time. And out here is probably material that came out in April and May. So it persisted significantly longer than anybody had thought. So we published this in Environmental Science and Technology, Fate of Dispersants Associated with the Deepwater Horizon Oil Spill. And this was also relayed to the public in what I think was a reasonable way. Chemical dispersants endured long after Gulf oil spill. Underwater dispersant in Gulf lingered. I think those are both quite accurate. So the next issue that we wanted to address, having figured out something about what was going on with the dispersant, was the biodegradation of hydrocarbons by bacteria. And we had been tracking this all along. This unfortunately doesn't refer to one of our papers, but refers to a paper by Terry Hazen at Lawrence Berkeley, or then at Lawrence Berkeley National Lab, where he had identified some very large oil-eating bacteria, very large being like 100 microns or something. But this was in the Houston Chronicle about that. And we'd been, both his group and our group had been looking at the microorganisms that were eating the oil. He just got the better cartoon. And so the way that we did this, I think is worth saying something about. We basically gave the bacteria what I call a neutron diet. And we took fresh seawater samples, and we fed them, again, this heavy isotope label, except this time just pure heavy isotope. And methane, ethane, propane, benzene, all in this case. And we let them eat that for a period of a few days or a week. And what we saw was that they consumed it. They respired it. That's all showing here. And then what we did was to take their DNA from them. So we kill them, we extract out their genetic material, their DNA. And then we use a Beckman product. I was taking the Beckman tour before this and had forgotten that we used a Beckman ultracentrifuge to do this. And what we do is that we take the DNA and we spin it down so fast that the heavy isotope labeled DNA separates from the regular DNA. And this is the same kind of thing that the Iranians are trying to do to purify their nuclear materials for whatever purposes they have. But in this case, our purpose is far less nefarious, was to identify which organisms were specifically eating each of these compounds, and we were able to do so. We published this in the Proceedings in the National Academy of Sciences late last year, Natural Gas and Temperature Structure to Microbial Community Response to the Deepwater Horizon oil spill. There's an interesting aside here that one of the main organisms that we identified, we saw very little of the giant oil-eating bacteria, few of them, but not many. The organism that we saw that was dominant belongs to a genus known as Colwellia. And that's named for Rita Caldwell, former director of the National Science Foundation, but currently she is the scientific director for the Gulf of Mexico Research Initiative, which is BP's $500 billion research initiative to understand the Gulf. So Colwellia, she's here doing the Gulf stuff, I don't know. It seemed a little suspicious to me. If I didn't get a laugh on that, I have to put a comment about, an exclusion so the lawyers don't ask me. Okay, so the last aspect of the science I want to talk about is taking these studies and putting them together. So what do you get when you put together the chemistry and the biology and the physics of what was going on in the Gulf? And so we have the wellhead up here. And I'm going to show you an area roughly about this size. That's a 50-kilometer scale bar down there. And what we did, I collaborated with Igor Mezik, who's a fluid dynamicist, to do this, because I could do the chemistry and the biology, but not the physics. And we combined the Navy's model for water movement in the Gulf of Mexico. It tracks thousands of individual parcels of water as they move around. We focused in, I should say, on that deep plume horizon at 1,000 to 1,300 meters. We put in the physics, where all the water's going. We then seeded that with first the chemicals that we knew were coming out of the well and getting stuck in this deep plume. There ended up being 22 individual chemicals that we tracked and 4 sort of categories that we added in. So 26 total categories of chemicals that were emanating and coming into these deep plumes. And we put in the rate at which they were coming in as we had determined from the other published literature that had come out. And then we seeded that further with a low concentration of bacteria, what we expected or thought the pre-spill condition would be. And knowing now something about the bacteria that had grown up, we allowed them to grow. So we put in the physics and let the water move. We put in the oil and gas at the wellhead, and the population was seeded, and we just let it do its thing. And so what I'm going to show you is a simulation here in a minute. It's going to look something like this, where there's going to be 4 different boxes. The top one showing you the hydrocarbon concentration. That's all the hydrocarbons added together. The right one is all the different bacteria. We individually tracked 52 different bacteria in the end because we had some ecosystem properties that we'd also uncovered that we put into this. And then the respiration rate, how quickly the oxygen was being consumed at any given time, is down on the bottom left. And on the bottom right is the oxygen anomaly that I talked about. So this is the one example model run. Which includes all the caveats. There we go. So there's the well, and that's the area. And this is just one box to remind us that we're just talking about the 1,000 to 1,300 meter slice of that deep plume. And you'll see up at the top in the middle, April 14th, 15th, 16th, 17th, 18th, Deepwater Horizon is going to sink here on the 22nd, and on, the hydrocarbons begin emanating into the Gulf. And so what you see are the hydrocarbons, the bacteria, and the response of the bacteria with the physics moving things around. And it was really the physics that taught us a lot of very important lessons here. That at the time we'd heard about these plumes, that there was a plume to the southwest, and people were arguing about where things were and what was happening. And the reality was things were all over the place. There was a lot of swirling. There were sloshing of water back and forth. That it was really very complex. And depending on where you poked your hole on the map with your sampling device, you could see something very different. And this probably shouldn't have surprised any of us, but being out there and doing the sampling, you think, I've figured something out, and then you piece it all together and go like, oh, wow, if I'd been 3 miles over, I would have figured something else out. And so here we see we're getting into August. The well had been shut here for a month. And what happens here that was interesting is that things no longer are really swirling as much. They begin to move in a persistent way down to the southwest. And this was the time that we were there, the September time, when we did those integrated oxygen anomalies. And we were very happy to see that this independent model showed that we were in the right place at the right time, because I didn't mention that there was quite a bit of scientific debate, vigorous debate about one of those papers. And so we published this earlier this year in 2012 in the Proceedings in the National Academy, Dynamic Autoinoculation in the Microbial Ecology of Deepwater Hydrocarbon Eruption. And this was also picked up reasonably well by the media and relayed to the public. In fact, they even used one of our model runs on page 3 in the Wall Street Journal, which I thought was kind of cool. Microbes team to clean Gulf, current cited in Gulf spill recovery. Now, we didn't say anything about the residual components of oil. And we were really looking at the active processes and the things we knew were consumed. And so I want to spend the last few minutes talking about sort of where we are now, the processes that are going on, and where they're heading. And this is not my own work, just a bit of a synopsis of what's going on now, as it has been 2 years. And so, yeah, those are all oiled animals that are spinning at the pump there. Since the spill ended, it's been a bit of a legal mess to try and figure out what's going on. There's quite a few lawsuits going on, including a large class action suit that's being settled. But lumped in with that is a significant fine for the release of the oil, which is also an issue that's being hotly debated. It turns out, my understanding, that when you have a release of this magnitude, you get charged somewhere between $1 and $5 per gallon. That's the difference between roughly $5 and $25 billion for the spill. And the amount depends on how good of whether or not you were negligent, whether you assisted in the efforts after the fact, things like that. I don't know that anybody ever pays the top amount, but it's somewhere in the middle there. And so that process is part of the same lawsuit in a different phase, and that's ongoing. And of course, there's the potential for criminal charges. None of that's been decided upon or announced, as far as I know. And so that we may also see that happen for company executives or people who made various decisions. But what I want to talk a little bit about is the damage assessment process, because I follow this more closely than I follow any of those legal aspects. This is the most complex damage assessment, as indicated by the complexity of this figure. This I pulled from a talk given last week in Santa Barbara by the director of the damage assessment process at NOAA. This is how they break things up and what they're trying to understand, and all these different technical working groups that are highlighted here. The natural resource damage assessment, it's a restoration process. It's going to go on, I think, for many years. The goal of the process is to compensate the public for the injuries to resources and lost human usage. There are many hundreds of damage assessments that go on every year. This is by far and away the most complex ever undertaken, far more complex than Exxon Valdez. The damage assessment, it's a legal process. And it comes from the Oil Pollution Act, as well as from the Superfund and Clean Water Act, is where it sort of gets its power from. It is a cooperative process, which makes it very interesting because that means that the responsible party, in this case BP, works with the federal government to study the impacts and to make the assessment of how much damage occurred. So they're legally against each other, but they're working together. And in some ways, it works out well. They use the same data. They approve, or they at least get to comment on each other's work plans. And ultimately, they end up on the same boats together. Multiple of my cruises, we had representatives from the damage assessment, and if they come, you have to have a representative from BP. So both would be coming in this cooperative process. In practice, that actually worked quite well because there are a lot of hardworking 22-year-olds that just got their first job because nobody was ready for this magnitude of a damage assessment. And so here, these are just all the different working groups and all the kinds of questions. There's fisheries questions, sediments, deep water sediments, water column. Every different animal has its own working group that might have been impacted, and many of them have sub-working groups. There are chemistry working groups and toxicity working groups with many different people involved. So this is a huge undertaking, not to mention how many lawyers. And so some of the issues that they're looking at, one of them is what's happening now on the shorelines. During the spill, it's clear where the damage occurred. There's still residual oil, and there's going to be a big debate about how much damage that actually is caused at the time and then continues to cause. This is an example. This is a picture I took on a beach in Louisiana where this is a tar ball. This is like a year and a half after the spill, and that's a tar ball from the Deepwater Horizon, and somebody driven over it, and I thought it was kind of cool the way they left their tire tread on this tar ball. There's a lot of this oil still there. It seems to be sitting in sandbars and offshore environments, and then storms and things will bring these up. Nobody has a good feel for what the actual toxicity or impacts of these things are, except for anecdotal arguments about, I live in Santa Barbara and I step on these all the time. So, we don't really know what their impact is going to be, and they could be different in many ways from other seepage-type events. So this is one issue that I think they're going to have to deal with. Another is natural seepage. There is an extraordinary amount of natural seepage that occurs in the Gulf. These are most of the 1,000 known natural seeps that are observed as oil slicks, persistent oil slicks on the surface by satellite. And so one of the questions that has come up is how does this event and the impacts of this event compare to the baseline of having this oil input into the Gulf of Mexico? And this is going to be debated. I do a lot of work in oil seeps, and you don't get much impact from oil seeps, primarily because the flow rates are so slow that you don't see much impact, but this is one argument. This was a seep that we mapped actually during the response efforts overlooking the Macondo wellhead. The ruptured wellhead was about 5 miles down in this valley, and this was a whole series of seeps that we ended up coming across. There have been many other impacts, and I think the last one that I'm going to mention, this is a paper that came out in the Proceedings of the National Academy of Sciences by Helen White and her group. I was not involved in this. And they're looking southwest of the wellhead, roughly 10 miles or so, and what they see is deep-sea coral that is covered in this sort of schmutzy stuff that they linked back to the Deepwater Horizon oil. Coral doesn't normally have this sort of black coating on it, and most of that coral is dead. The reason that people are paying so much attention to this is because deep-sea coral lives for several hundred years. And when you decimate a patch of coral, the time to grow back is extremely long. And so the killing off of coral in the damage assessment gets a multiplication factor of its age. So it's a big multiplication factor, and it's a somewhat rare deep-sea community. So that got a lot of attention. And the very last thing I mentioned, and maybe this is where it's not all bad news, is that at the time of the, in September of 2010, I was out on the water actually coring. There were a number of, the UGA Gulf blog and a lot of media picked up about thousands of square miles of the slime highway, I think they called it, where oiled sediment had fallen all over the Gulf and was suffocating things, and the image on the left was one of those images. It turns out there's yet to be any evidence
published to support that assertion, and the analyses that have been conducted aren't showing any oil in those sediments. In fact, that top layer of sediment that was indicated to be oil, it appears to be very common throughout the Gulf of Mexico. And it has to do with burrowing animals and other things. The image on the right was taken 75 feet, within 75 feet of the image taken on the left, but a year and a half later, and it looks like many other images that were taken in clearly non-impacted areas. It also shows burrowing animals that are living here in the sediment happily and other things that look like they're alive. So the suggestion from this and from other work is that there's not this thousands of square miles of wasteland. There are undoubtedly impacts. I don't want to say there aren't. There are probably pockets of contaminated sediment out there that people are looking for, but it's perhaps not as dire as some of the proclamations that were made during the spill would suggest. So with that, I will thank you all for paying attention, staying awake.